keep track of stuff. So we're going to look at mainly Kepler's laws, and Kepler's laws stem from Newton's law of gravity. So Kepler's laws all came about as a result of Newton's laws, and specifically Newton's gravitational law. All of the celestial bodies, all the planets, all the stars, all the comets, meteors, anything traveling through space, they all abide by Newton's law of gravity, and Kepler came up with a couple other laws, came up with 3 of them specifically to talk about planets and their orbits. Okay, so we're going to specifically look at those. The first one, so let's start off with this first law here. The first law is kind of obvious, but you've been almost misled your whole life. If you think back to like your 4th grade textbook or your 5th grade science textbook, when you saw the orbits, you always saw ellipses, like this on the far right. And that is the actual true law. The first law says the planets follow an elliptical shape in orbit, where the center of the sun is what's called one of the focal points. There are 2 focal points because there can't be just one center for an ellipse. But it turns out, if you look at this diagram here, the first one is actually the Earth. The Earth, although it travels in an elliptical orbit, is very, very close to being a circular orbit. Other planets, as you can see on the far right, for example, Pluto, follow a much more eccentric elliptical orbit. E stands for eccentricity. This little E down here stands for eccentricity. And the closer your eccentricity is to 0, the closer the shape is to a perfect circle. So if you were to just arbitrarily try and draw a circle on the board, or just try and draw a circle in general, there's a good chance it's not going to be a perfect circle. And if you look, and you'll notice, you can measure a diameter here. Well, first of all, you have to try and find the center. But you can try and measure several diameters. And what you'll notice is that those lengths might be a little bit different. So the eccentricity of a circle has to do with how close it is to a circle, really. Or the eccentricity of a closed loop, you could even say. But generally speaking, planets in general follow elliptical orbits. Okay, but the Earth is so close to a circular orbit that we could almost say it's a circle. And it's so close to that value. And you'll see how that affects us, actually. It affects seasons, it affects temperature, a lot of stuff. The seasons come about mainly from the tilt of the Earth, but we'll talk about that in a little bit. So if you've ever seen Pluto's orbit, and you look at the actual solar system and the way planets pass one another, you'll see that some orbits actually even overlap. If all of the orbits were perfect circles, there would be no overlapping whatsoever, because you would have a bunch of rings of concentric circles. Right? Imagine the sun being the center and having these rings of circles as you move out, right? Mercury, Venus, Earth, Mars. You move planet to planet, the shells of those orbits would get larger and larger, the circumference. But because the shapes of the orbits are not perfect circles, we have ellipses, so sometimes the orbits will pass through one another. And you see that a lot specifically. Is Neptune considered a planet nowadays anymore? Is it back to being a planet? Because for a while it wasn't a planet, right?
What do you mean Pluto?
Wasn't it Neptune that they categorized as something new?
Pluto's a dwarf planet because its moon is almost the same size as it, so they rotate around each other
With like
as it goes around, and that's what gives it that weird oval orbit.
Yeah, this section is just eccentricity. That's really. I didn't even know you knew that. It's great facts, and it's exactly what he's saying is right. It has to do with 2 things that are close in mass. So think about the Earth and the Moon. The Moon is much less massive than the Earth. So the Moon naturally goes around the Earth, whereas Pluto and its Moon, they kind of they orbit each other. And there's a term for that with who would know that? Older Scarangello, Anthony's older brother, is actually studying this in college right now. He's studying what is the topic actually called? Astrophysics would be the name, I guess. But physics of celestial bodies. But when 2 things orbit one another is a different name for it, and that's what you're talking about with Pluto. So wait, is it considered a planet then or not?
It's a dwarf planet.
So does that make it a planet or not though?
That's just what it's classified as.
Okay, so do we have 9 planets though at least?
Yeah.
Anyhow, the idea again though is that the actual orbits are elliptical shapes with different eccentricities based on that planet. Okay, based on that actual planet. The second law, and this is one that is very useful to understand how the velocity of a planet changes, the velocity or the rate at which it travels around the actual sun, maybe its orbital period you might call it. And the way this is thought of, and it's a little bit confusing with the diagram. So the diagram on the left shows the Earth with its actual shape, and this is really exaggerated on the far right. But it's easier to see with the well, not necessarily easier, but It's a lot more exaggerated over here, so it's easier to make the point. But what you're seeing here is this. Think about this as the Earth, okay? And the Earth is traveling around the Sun. The Sun is at what's called one of the focal points. The other focal point is empty space. Here's the other focal point. I'll put an X there. Okay, so every elliptical orbit will have 2 focal points. You'll learn about ellipses this year in your 4th quarter, most likely, of math. It's either 3rd or 4th quarter. I know you covered it as a topic, though. So an ellipse has a major and a minor axis. So we have our 2 focal points there. And if you look at only the sun as a focal point, and you draw a straight line between the sun and the planet, so just follow where I'm pointing, draw a straight line between the sun and any given time the planet has a certain location, what turns out is this. Each time period that elapses from segment to segment or snapshot to snapshot is the exact same amount. Yet it moves a shorter distance here than it does over here. And the reasoning is because the area of the sector, remember from geometry last year, they were called sectors, like a slice of pizza is a sector. So the area of the sector for each time period has to be the same. And the area of the sector is not equivalent for each of these time periods in the sense that the arc length is the same because the sun is not actually at the center. If the sun were at the center of a circle and you cut it into 12 pieces, then each piece would be literally identical in shape. And you could see that with a pizza. Okay, take a circle, literally just cut it in 8 pieces. Each of those sectors are absolutely identical. That's the whole idea. Oh, it's most of these, except when you get those pizzas, right? You get like the small slice. That's always a terrible feeling. The big slice. So these 8 slices should all be identical if it's a circle and it's cut into 12 equal pieces. But over here, what we're seeing right away is that these areas or these sectors, they look different in shape. But it turns out that the area of each sector is identical. So this area over here, this is a much more exaggerated version, but this area over here, A1, is equal to the area A2. It's like saying, if you recall, like if I had a rectangle that was 2 by 4, I could also have a rectangle that's 1 by 8, and they'd have the same area, right? 1 by 8 is 8 square units, 4 by 2 is 8 square units. So if you had rectangles that were exaggerated, one was stretched, they could still have the same area. That's what's happening here with these 2 areas. These values are absolutely identical. So it takes a planet, say, 45 days to go this far. It's going to take the planet 45 days to go this far. It's the same time period of elapse. So as a result, if the same time period elapses, you can easily conclude that it's traveling slower here and faster over here. Think about that example with the merry-go-round, with the horse on the outside traveling the same angle, like one cycle. The horse on the inside is traveling the same angle, like one cycle or 360 degrees, but the outer horse travels a lot further than the inner horse does. And we talked about that with track. We said how track runners start at different parts because the outer lane takes the longest. Well, technically here, you could think of this right here, right? This is a shorter distance right here than this distance traveled if you literally were to measure this curve. So if this travels a shorter distance in the same time period, it must be going slower over here. It's going slower over here when it's further from the sun. And it's going faster when it's closer to the sun. Now, also use common sense. You study Newton's law of gravity. Newton's law of gravity affects the gravitational pull, and we talked about how when 2 things are closer, there's more of a pull between them. So if you think about like the Earth and the Moon are very close to one another. So the gravitational pull between them might be larger than the sun and the moon. It turns out not because of the mass that affects it also. But if you think about this in this case, well, this planet, whatever it is the same planet in both cases. When it's further from the sun, the pull on the planet is not as strong, so it's going to travel slower. When it's closer to the sun, the actual sun is pulling it harder with more force, so it will travel faster during this period. So when it's closer to the sun, the actual planet travels a lot faster than when it's further from the sun. That's literally what Kepler's second law is telling us. Another interesting thing, something that I always mention every year, because the only reason I mention this is because it's one of the biggest misconceptions most people think that when we're closer to the sun, we're in the summer, which makes sense logically because you think, oh, it's warmer, you'd be closer to the sun. But that's not the case, actually. And you could really recognize that because think about when we're closer to the sun, say it were summer, hypothetically for us, in the southern hemisphere, what would it be? Yeah, we know that the hemispheres have opposite seasons, right? When it's winter for us, it's summer for the southern hemisphere and vice versa. So it doesn't make sense to say when we're closer, it's summer because which half of the earth is it summer for, really, right? Is it the northern or the southern hemisphere? So really what happens is this, and I'll draw a little figure on here of the earth. So when we're closer to the sun, it turns out that the southern hemisphere is angled toward the sun. So for example, if I draw the earth right here, and I were to draw my axis of rotation, okay, that's the equator right there. Here's the North Pole, and here's the South Pole. So it's rotating about that dashed line. So this dashed line is the way that the earth rotates. Here's the North Pole, and here's the South Pole at the bottom. So what you're seeing is that the sun's rays are hitting the southern hemisphere in a more direct way. In earth science, there was an acronym, I still remember to this day because it was always a weird acronym. It's not a real word. Insulation, but spelt not like insulation in a wall, spelt with parts of 3 words. Incoming solar radiation. It was a phrase in earth science you have learned at some point that has to do with the sun's rays and the angle at which they hit the earth. So at this point in the year, the southern hemisphere is getting more direct rays from the sun than the northern hemisphere. That's why the southern hemisphere has summer at this time. We, although closer to the sun, have the winter in the northern hemisphere. Now, when Earth goes all the way around, it's still at the same angle. So when we draw Earth on this side now, it's still drawn the same way. It's still rotating about that same axis with the southern hemisphere at the bottom and the northern at the top still. So now what's happening is when we're further from the sun's direct rays hit the northern hemisphere, and the southern hemisphere doesn't get those same direct rays. It gets rays at a acute angle, a lower angle. And if you think, we're going to learn this year about what's called light intensity in this second semester when we get to light and optics. A more direct angle has more of an intensity. How many of you, well, everybody's used a flashlight before, but how many people have ever seen this? If you take a flashlight and hold it against the wall, and then you turn and hold it against the wall, what happens to the light showing up on the wall? Imagine it's dark in the room. I hold the flashlight directly at the wall, so the light rays are perpendicular to the wall, and then I hold it over here, and the light rays hit the wall like this. What happens, Marilyn?
It'll be like slanted, right? It'll cover more space.
It covers more space, and physically, the light itself, the color, the intensity, what does it seem?
Lighter.
Yeah, it seems less or lighter, not as bright. If you were to hold a flashlight directly at the wall in front of it, you see a much brighter spot appear than when you hold the flashlight at an angle from the side. It's because those rays are being spread out more, really, the intensity of the rays. So it turns out that although we might think, when it's warmer, we should be closer to the sun because the sun is what gives us warmth, it's not true. Okay? In the southern hemisphere, it's true. In the southern hemisphere, they have summer here and winter here. So for the southern hemisphere, that common misconception is not a misconception, actually. Okay, but for the northern hemisphere, it turns out that we are in winter when we're closer to the sun because of the way that the earth is angled. Do you know what the angle of the earth is? Anyone know that number? It comes up a couple times. There's a reason for it.
Isn't it a 43 degrees still?
Close, not 43. No, I checked with the 3 there. Much, much lower though. It's 23. About 23 or 23 and a half. It comes about also, if you've ever looked at are any of you good at geography? You know your lines of latitude? So the equator obviously splits the earth. What are those other lines of latitude that are kind of the important ones that we talk about?
Like the angle of the equator makes it,
But what's the name of them, I'm saying? And where are they located? Anyone ever seen the terms? So you could have like 0 latitude, right? Then 10 degrees latitude, 20, et cetera, et cetera. But what I'm asking you, what's the other 2 lines that are? Yeah, the tropics, Cancer and Capricorn, right? Those angles of latitude or those locations of latitude come from the Earth's tilt. The values that they come about are derived from the fact that the Earth is tilted. If we weren't tilted, what would happen? How about that question? If the Earth was not tilted on an axis, what would happen as a result, Gus?
Then it would just be like the entire west side of the world is like.
Well, it's spinning though.
Yeah.
It's spinning. So what would happen though physically to the Earth?
There wouldn't be many seasons.
There wouldn't be, not many, but there wouldn't be any seasons. Imagine if the Earth, okay, is, let's draw it in red now. I'm going to make it much bigger so you can see the exaggeration. Imagine the Earth is rotating. Here's the northern and here's the southern hemisphere. Northern pole and southern pole, rather. So we have the bottom half as the southern. Well, it's spinning this way, right? The Earth is spinning this way. The equator would always be getting the most intense rays here. Okay, the equator itself. And then the Earth is itself going to rotate around the sun. I'm trying to draw, it's hard to draw this, but imagine the orbit of the Earth would be going into the page like that. Okay, here's the Earth traveling like this around the sun. So the equator would be getting those intense rays, whether it's on either side, and the poles would always be very cold. Whereas, they still are cold, but whereas now, what do you know about the northern and southern pole during certain times of the year? It's very interesting. Anybody know any facts about the northern and southern pole at specific times? Mike?
Well, I know in the winter and the hemispheres, there's no light.
Yeah, there are times of the year where you literally have 24 hours of light and 24 hours of darkness above a certain latitude. Again, where does that come from? The angle of the Earth is what creates that. So had we not been on a tilt, our axis, for some crazy reason when the Big Bang occurred a long time ago, and the Earth suddenly was on this tilted axis, we would not have any seasons. It wouldn't even exist. And that would change the environment of the Earth dramatically. You guys know, just think about food. Certain food is not in season at certain times. You ever go to get fruit and you're like, oh man, the fruit looks terrible right now or something. It has to do with the actual weather, obviously. It has to do with the seasons. So without seasons, we'd have a lot less variability in the Earth. But seasons are part of the Earth that make it unique and make it partially habitable too. So the idea here, two things to remember. The Earth's speed changes as it gets closer and further from the sun, and the seasons are created by the tilt, not the actual location of the Earth around its orbit. Okay, those are the two main things you want to take from there. Let's take a look at our third now. The third law, so the first two are really just conceptual. There's no math involved. Okay, they're really conceptual. But the third one has a little bit of math. And the third one is really interesting. This can be proven mathematically. But it was discovered initially, it was discovered empirically. What does that mean, empirically? What does that mean when it's discovered that way?
At the lowest numbers.
Okay, that does also mean empirically, yeah. Sorry, maybe that's not the right word then. I'm thinking that empirically also means based on data alone. So I could say, I guess maybe experimentally, because the empirical formula in chemistry was like the lowest possible values, right? It was like simplifying things the most. So maybe I should use experimentally. I feel like empirically also works. Well, these values here that we're seeing on the far right, take a look at these values. These are what were discovered. This t squared over r cubed. So let's discuss what this is. So the third law says the following. If you look at any planet in the solar system, any planet whatsoever, the value of the period of the planet's actual revolution around the sun divided by its average distance from the sun, and that value is cubed, the actual period is squared, always turns out to be a constant. It always turns out to be like a guaranteed value. And what's interesting to see is that, Mercury takes a lot less time to orbit the sun. Why? Because it's closer than Earth is. Right? Look at all these values. What is it, AU? Anybody know the term AU? Not HAU, but AU. Astronomical unit. I felt like I was like an AU. An astronomical unit. An astronomical unit literally stands for the length between the sun and the Earth on average. So every other value in this table is all based on the Earth. We're very self-centered. We base everything off of us. So we see the periods also. The periods, notice, are based on years. What kind of years? Earth years. So what you could say, actually, if we go down a little bit further, is that one Pluto year is equivalent to 248 Earth years. So in the time it takes Earth to go around the sun 248 times, Pluto has only gone around the sun once. Why? Because it's further away. Where do we see that? We see that with our AU value, or our distance. Pluto is about 40 times further from the sun than the Earth is. So that's why it takes forever to get probes and satellites and all these other things that we can study other planets with out to that area. I mean, it's only until, I don't know how long ago, but Jupiter has been really studied a lot more lately because of the fact that our satellites are getting closer and closer and able to actually take data. This value is about 40 times as far as the Earth away, and it takes about 250 times as long to revolve around the sun. But what you'll recognize is for all of these values, if you take the period value and square it, and then divide it by the average distance cubed, you'll get a constant value for all of these planets. So if you're one of Earth or one of the solar system's planets, you can do this for any values, for any unit you want. So I have these in years and AUs. Above, it's measured in seconds and meters. Either way, if you take the time period squared over the average distance cubed, you're going to get a constant for all planets. Okay, and I'm going to prove this in a minute to show you why it comes about. It comes about from Newton's law of gravity, again, as all things here come from. But the idea here is that this value is constant the entire way through. So if you were testing to see if something were a planet or were a planet that followed all of our laws, it's a simple way to judge if something does classify as a planet. So Gus, back to the question that I asked when you answered with Pluto being considered a dwarf planet. I have a feeling, I don't know for a fact, I guess I could probably look it up, but I have a feeling that because the values matched up here, Pluto was categorized as a planet. Because it does indeed revolve around the sun, right? Pluto does revolve around the sun, and it does fall into the category where the period squared over the average distance cubed turns out to be the same constant as the other planets. So categorizing it as a planet does actually make a lot of sense. Now, the other way of categorizing it had to do with, as you were mentioning, the size of the actual moon itself. But these values squared over these cubed will always give you that same constant. So this is the third law from Kepler. Very minimal math. If I ask you to do something involving this, I might ask you to show that this law is true by making these calculations, giving you values, or maybe I'll give you maybe a sample planet without a name and ask you, is this one of the planets that revolve around the sun? How can you check? Well, if I don't give you the name and call it like planet X, but I only give you values, you can find the period squared over the distance cubed and compare that to, say, the Earth's. If the values are the same, then you could say, you could conclude it is one of the planets. Matt?
The main part of the math on the test is going to be from the last.
Yeah, I mean, from this law it would come from, and it would be literally taking period squared over average distance cubed and seeing if that is one of those values that's constant along the way. So if you were given a random number, you got to check to see that it matches up to what the Earth's would give you. Now, please write a little note that this is not radius. We've had R 3 times now. R for torque was the lever arm. R for Newton's law of gravity, 4 times, I'm sorry. R for Newton's law of gravity was distance from center to center. R from circular motion was radius. Now this R, although it's really distance from center to center, it's the average distance from center to center. And why am I saying average distance? Because according to Kepler's laws, we just found out that planets are sometimes further from the sun and sometimes closer. So if I'm the sun and I'm over here, and I look at an exaggerated orbit, well, when the planet's out here, it's a lot further from the sun than when it's over here. So how could you use a value? There's no such thing as a radius here because it's not a circle. So what we have in this column, right, what we have in this column right here is called the average distance. So it's taking all of these lengths, adding them all up, and dividing by as many as you have. You wouldn't actually do that. You would use calculus to actually compute the value. Okay, you could use calculus to find the exact average value. But if you think about it, take this distance, plus this distance, plus this, plus this, plus this, right? Take all these distances, put like an infinite amount of lines connecting the sun to the actual planet, as many as you can, and then take all of those lines and average out those distances. That'll give you the values seen in this column here. Okay, so R is many things on this next test. It's a lot. Lever arm for torque, radius for circular motion, distance from center to center for Newton's law of gravity, and average distance for Kepler's laws. Okay, that's why I really always focus on telling you guys, you got to know what your formulas mean, what each variable means in the formula, what the units are, when you're going to use the formula. That's why it's important to understand and study your formula sheet. Okay, because those values take on different things depending upon the scenario. R could be 4 different things as we're seeing here. 4 different values in the next test, R could be defined as. Let's quickly prove that this is actually true. You don't have to write anything. You can just watch. Okay? There's no need for you to write anything down. I'm just going to go through this proof real quick. If we think about the force that's keeping the Earth in orbit, what is that force that's doing it? What's the force that keeps the Earth in orbit? Gravity. And we know that the force of gravity is G m1 m2 over r squared. Now, r is the distance between center to center between any given planet and the sun. m1 and m2 are some planet and the sun respectively. And g is the gravitational constant. Now, we also know that when something moves in circular motion, the equation we can use is mvt squared over r. Now, we haven't really emphasized this, but m. Is m the value of the thing that's in the center or the thing that's doing the orbiting? In the second formula here for Fc, is m the thing that's going around in a circle, or is m the thing that's in the center of the circle? What is m? Which one of those? Travis, what do you think? Going around? How do you remember that? You're right. How do you remember that? Think about where we use this formula to help answer that question. Yeah, whenever we did this formula, it was always the velocity of the object moving around, the mass of the object moving around. Did it even have central object usually? No. It was like, remember, we're spinning something on a string, or you have a car going around a track in a circle. M stood for the mass of the car, whatever the object was that was moving in circular motion. Well, in this case, is the sun moving or is the planet moving? Which one? I'm only hearing Trooper, right? It's pretty obvious. I hope we all know from middle school science what kind of a galaxy are we in. What do we call it? What is it? Thank you. Heliocentric, meaning helio, sun, centric, centered, sun-centered. We're in a sun-centered world. For a long time, what did we believe it was? Yeah, we thought it was geocentric. A lot of people thought it was geocentric, and then scientists started proving it untrue. And unfortunately, the Catholic Church was like, no, we are the center. We have to be the center. It doesn't make any sense. So then there were big battles between scientists and stuff. It was a big thing, actually, for a while. Until we finally realized that the physics is true, that we are in a heliocentric universe, or heliocentric galaxy. What's that? A lot of people died as a result of this argument. Yeah, a lot of people.
I don't think Galileo was killed, though. I think he just died of old age.
I don't know if Galileo was. I'm just saying a lot of people died as a result of this. There were people that were persecuted because they believed and they were saying it's heliocentric when the scriptures had said it's always geocentric, and God had said that, and people argued with that idea. So this is what we've got as a result, right? M1 is the mass of the planet. That's showing up here. Now, if gravity is keeping something in circular motion, we could say that it's gravity that's causing it, so we could set these things equal. And we could say, well, these have to be equal to each other simply because of the fact that the value of the force that's being pulling us around equals the value of centrifugal force. It's always providing it. And what do we have on both sides? We've got M1 on both sides, so those both drop off. We've got an R. At least one of them, right, drops off. So I could go ahead and just cancel this R with the square term, which leaves an R below over here, which makes my formula a little bit easier to work with. And we're going to use this formula, actually, the exact one you're seeing now, in a minute. But before we get to that, we have to consider, well, what is velocity really? When something moves in a circle, how would you measure the velocity, or in this case, really, the speed of something moving in a circle? How do you measure the speed of something? Anything. Speed. What is it? Distance over time. What's the distance traveled for something that's assumed to be moving in a circle? What do we call the distance traveled? What's the word for that in geometry? Circumference. So the distance traveled is the circumference. The time it takes is the time it takes an object to travel around, or its period time. Again, we're using the Earth because the Earth is so close to a circle, we can assume it's moving in a circle. It's allowable. So it turns out, and that's why those figures were a little bit off, the decimals were off because of this. So we could say, well, velocity, or in this case, orbital speed, is really circumference over the time it takes. Now, if we look at this formula a little bit further, we have G m2 over r, I'm going to square everything. Again, you don't have to write this down. Just watch so I can show you where it comes from. And then the last part, what we can recognize is this. If I multiply by t squared, I want to bring t squared up over here by multiplying by t squared. And I'm going to bring r squared down here by dividing by r squared. It'll give me t squared gm2 over r cubed equals 4 pi squared. And then if I want to get rid of gm2, I can divide by gm2. And I get the following. Now let me explain why this is the big conclusion right here. T squared over r cubed, that's what we just had a minute ago. If you look at Kepler's third law said take the time period squared over the average distance from the sun cubed and you'll get a constant for all planets. How can we prove that that's true? Well, look at this. Pi. Do you know what pi is? Yeah, 3.1415, right? It's a constant. G, what is G called again? Anybody remember the name from last section we just did? What's the name of G? What do we call it? It's not Earth's gravity. What do we call it? What's the word? The what? Specifically though, universal, right? It's the universal gravitational pull. It's a constant anywhere in the galaxy. The mass 2. What did mass 2 represent? That represented the sun's mass. Isn't the sun's mass a constant? Well, let's assume that we're not losing any mass due to the reactions occurring. These are all constants. So it turns out that tau squared over r cubed can be proved to be a constant. If you were to literally calculate this value, you will get one of those two numbers from the last table we just had a minute ago. So anytime you look at the time it takes a planet to revolve squared over its average distance from the sun cubed, you will get some constant that's the same for all planets. That constant is 4 pi squared over gm of the sun, over g times the mass of the sun. Okay, so all this is showing you is that Kepler's third law is indeed true, that all of these values, t squared over r cubed for any planet, is equal to a constant. Okay, it's going to be the same for all of the planets. You don't need to be able to recreate that or show me all of that again. I just want you to see that when we look at this ratio, it's got to be equal to a constant, and you can prove that mathematically here in series. Let's talk for a little now about satellites for a second. For the most part, students understand satellites to be these mechanical objects that are up in the sky that give them a cell phone signal. I mean, for the most part, that's how you think of satellites. I mean, you get a lot more than that from satellites, but what I want to get at is that a satellite is not only things that are mechanical. Those are just man-made satellites. A satellite in general is something that is orbiting a central object. So the moon is a satellite of the Earth. Technically, the Earth is a satellite of the sun, etc., etc. So when we're looking at these, we're looking at things that actually revolve around one another, not necessarily just man-made things that revolve around one another. And what's interesting, actually, is the way satellites actually work. And this is what I want to focus on for this part. Satellites work just like projectiles, turns out. And it's really hard to understand, but let's think about it for a minute. If I were to, let me think if I could throw something that's easy. Right. So if I'm going to throw this marker across the room, if I were to try and throw it horizontally, okay, I'm trying to throw it perfectly horizontally, what happens eventually? It curves toward the end. We also have curvature. Now, it turns out on the Earth, due to Earth's gravity, if you launch anything horizontally, every 8,000 meters travel, it falls 5 meters. This is the curvature of the actual Earth. For every 8,000 meters along the horizon, the Earth curves down by 5 meters. Now, that fell about 2 meters, right? So about half of the 5 meters that it's falling, we're saying the Earth falls 5 meters. As you move across the Earth, it falls 5 meters. That moved almost half the distance down. Did it travel 4,000 meters though? How far did it travel across the room? Maybe like 7 or 8 meters. Not far at all. If I could throw something fast enough that it would travel 8,000 meters before it even fell 5 meters, it would just keep falling and keep falling and keep falling, and that's how something orbits the Earth. So what's called the orbital velocity is something that's necessary to keep an object moving at least 8,000 meters every 5 meters of falling. So I threw that marker, and it fell 2.5 meters, which is about half of this fall. So I should have thrown it 4,000 meters if I wanted that marker to continue to orbit the Earth. Is that possible? No. A human being cannot throw something 4,000 meters. We're talking about 4 kilometers. 5K is 3.1 miles. That would be taking a ball or an object and throwing it 3 and change miles. You just can't do that. So obviously, what do you need? You need more power, more energy, more force, more velocity. All these things are, in a sense, analogous to one another, or synonymous, really, in this case. So if you could throw something fast enough to make it travel 8,000 meters, and before it even falls 5 meters, it will orbit the Earth indefinitely, provided that it can keep that velocity the whole time also. So we talk about something called an orbital velocity. That's how geosynchronous satellites work. If you know, I don't know if you know anything about satellites, some satellites move with the Earth and some don't. So as the Earth rotates, okay, imagine this satellite is moving with the Earth perfectly, and it's staying right above North America the whole time, the entire time up. Well, as a result, it's called a geosynchronous satellite. Geo meaning Earth, synchronous meaning synchronized with the rotation of the Earth. Now, geosynchronous orbits are at different elevations. Based on the height that you're at, you have to travel at different velocities. And we're going to see in a minute, we'll derive a formula for that. But if your satellite is further away from the Earth, you might have to travel faster or slower than one that's closer to the Earth. If you've ever even thought about satellites and how it works for GPS, this is exactly what happens. There are 24 satellites that use the entire Earth's global positioning system that exists. 24 of them. And all you need are 3 to triangulate. Hence, triangulate. Ever heard that term before? When you hear anybody ever watch 24 or any of these kinds of shows where it's a lot of advanced technology and somebody has to save the world from some terrorist act or something like that, right? Well, a lot of the time they use the word triangulate. Now, can you triangulate the position? It's not a coincidence that tri means 3, triangulate. You need 3 satellites to determine where an object is. The 3 satellites can each determine what's called a locus of points around the Earth that it might be. So, for example, satellite number 1 will tell you it's somewhere along this circumference of the Earth. Satellite number 2 will tell you it's somewhere along this circumference. Well, this circumference and this circumference meet at 2 spots. So again, follow me, right? This circumference and this circumference of the Earth meet at 2 locations on the Earth. Well, which one is it? That's why you need the 3rd satellite. A 3rd satellite will give you a pinpoint of this actual location. This is something that's in your book, actually, about GPS and triangulation, if you're interested in it. It gives you a little bit more detail about what's happening. But satellites in general are just projectiles that are traveling at such a fast pace that they're able to move horizontally enough before they fall to the surface. What happens if the velocity becomes too little? The satellite will what happen? Yeah, it'll drop and crash into the Earth. If it's too fast, what will happen? What do you think will happen if the velocity is too fast? Yeah, it'll actually escape Earth's gravitational pull, and it will not remain in orbit. It'll go off into space, and due to inertia, it'll continue forever. So it turns out that with satellites and these objects, it needs to be a specific velocity every time. So let's quickly derive that. And this one I do want you to know. It's very easy to use. I'll give you this. This formula is not on your formula sheet because it's not one of your fundamental laws of physics, but I'll give it to you on the test if needed. Okay, I'll provide the formula. But it's the same derivation as the last one. We set circular motion, right, centripetal force, equal to the gravitational force. It's literally the exact same starting point as the last derivation we just did. And now all we have to do is cancel m1 and m1, cancel this r with this r squared, which leaves us with vt squared equals g m2 over r. And then to get the velocity, just simply square root both sides. So if you want to actually get a satellite up in orbit, you need to be moving at a velocity that is equal to the square root of g is a constant. What is m2 in this case? What is m2? Yeah, which one? The object moving or? It's the central object. Take a look, guys. M1 canceled, right? M1 was the thing that was orbiting. The central object, look at the definition at the top. The central object was M2. So this mass right here, M2, for Earth's satellites, M2 is the Earth's mass. So if you want to launch something up as a satellite of the Earth, m2 is the mass of the Earth. If you're looking at the satellite of Jupiter's, the satellites of Jupiter, because Jupiter has like, what, 27 moons or something? Jupiter's moons would use the mass of Jupiter to actually come up with the velocity, to calculate the velocity. What is R again? What is R again? For Newton's laws, what is R? So we're going to use
Distance of the center of the Earth to you.
distance from the center to the
To the center.
to the satellite. Good. Now, that explains why, ready? Here's the center of the Earth. Here's the Earth around it. Here's the satellite. Imagine the satellite is on the surface, like right above the surface. And now the satellite moves a little further. You're increasing the R value by doing that. By moving the satellite into a further altitude or further out into orbit, you're increasing the R value. By increasing the R value, what are you doing to V? How are these related? Come on. Yeah, very good. Decreasing, because they're indirectly related. You're doing this in math, I know you're doing it, we've been doing it all year and here. These are indirectly related to one another. So if you increase the orbital height of a satellite around the planet, you're decreasing the necessary velocity. And that makes sense too, because think, if the object's closer to the Earth, Earth could pull it much easier. So you got to have a lot of velocity to overcome what the Earth is pulling you down with. But if you get further and further and further and further from the Earth, gravity becomes weaker and weaker, and you don't need as much velocity. You need less and less velocity as it gets further. So this general theory here is what I want you to get at, what's boxed in. That M is the central object, so this is independent, let's write this down, right? Independent of the satellite's mass. That's the really interesting part here. So if I send up a huge satellite versus sending up a little probe, the mass of that object has no significance on the answer. Okay? This is independent of the orbiting object, the satellite itself. Okay? It's independent of the satellite's mass. And this is what, just to show you a quick figure, because I was demonstrating with my hands, but here's the Earth. So a satellite might be like, right, to draw a satellite, just draw a bow tie, by the way. It's the easiest way to draw it. Satellite might be there. But then suddenly, maybe there's another satellite that's a lot further away. Well, what are you doing? The R value is from here to here. But now the R value changes from here all the way out to here. So depending upon how far out the actual satellite is, the satellite moves slower or faster. Okay? It was a bit quick, I know that. Your homework for this is simply a worksheet. It's not out of your text. The worksheet is under Documents and Handouts. Okay? The worksheet is under Documents and Handouts on Moodle. It'll say 9-4 homework worksheet. And it'll clearly tell you.